It's my pleasure, and I'm very happy to introduce to you Hannes Kaufmann. He is a full professor of Virtual and Augmented Reality at the Institute of Visual Computing and Human-Centered Technology at TU Wien. I know Hannes since probably 20 years or more. I think, and you can correct me, Hannes, when I'm wrong, you did your PhD, habilitation, and also masters at TU Wien, right? So
yes,
always.
But I did my master's in geometry, so I studied mathematics and geometry with the goal of becoming a teacher originally. And
then you did a lot of research in virtual reality being applied to education.
Yes,
I guess. And so Hannes is one of the, say, key researchers, definitely here in Austria, but probably also in Europe and internationally in terms of, he's doing a lot of virtual reality. He did a lot of augmented reality together with Dieter Schmalstieg many years ago. And he's still doing VR mainly at the moment, I think. Your title is Large-Scale Walkable Virtual Reality. And we're looking forward to listening to what you have done so far in this area.
Thank you very much for the kind introduction. Let me share my screen. So thanks again, Oliver. Yes, I'm working in this area for over 20 years now, as do you. And today I would like to talk about work we did in the last few years, since 2015 mostly, in large-scale walkable virtual reality. And in the beginning, I would like to define the field where we are working in. I'm not sure if everyone is a domain expert here. And then I will motivate the problem and describe different ways for single users to walk in large-scale virtual environments. And then I'm looking at multiple users. So what is the difference when multiple users explore large virtual environments? What things are to consider there? And finally, I'm going to talk about haptics. Haptics also in large-scale VR. We have a big project going on in this area. Mixed reality, as defined by Milgram in 1994, is a continuum. Mixed reality contains everything between reality on the left and virtuality on the right. The work that I'm presenting you today is more to the right, but all of these mixtures of reality and virtuality are included in mixed reality, including augmented reality, augmented virtuality. So just to know the terms, I'm mostly talking about virtual environments today. And when we build such a system, such a virtual reality system or a mixed reality system, we always work with different components. It's a complex system. There is always a rendering component. Some form of visualization is always needed. There is always a localization component, tracking. We need to know where users look. Typically, there is interaction. Here we see some examples of work that we have done in the past. When it comes to rendering, we did ray tracing in AR in 2012 already. Tracking, we have developed our own tracking system over the years, and I will also present you the one that we're using now in large-scale environments. Interaction, haptics, for instance, that we're doing now, but we have done a lot of interaction in the past. And distribution, of course, when it comes to multiple users, multiple people are interacting, you need to have a networked system. Some people may be local, some people may be remote. They are all working together. And that's collaboration, to work together. Big challenge for the next years will also be authoring. We have done a couple of projects in this area because VR and AR hardware is not the most expensive these days. The most expensive when you're building such a system is content. Creating content, generating content, and how can this be done automated, semi-automated, or faster than it is done now. And of course, we also look at perception, and I will present some studies that we did, how users perceive large virtual environments and walking in such environments. Today, I mostly focus on this green part, interaction, distribution, and perception. So Did you ever want to walk through the pyramids, maybe inside? Did you want to walk through the Guggenheim Museum and see the art, or through the Hermitage, or visit Sixtine Chapel in Rome? What about walking through all these places in one day? Well, you might say, in reality, it's quite difficult to visit all these places and walk through all these places in one day. What if we could simulate these environments as realistically as possible in a virtual world, and you could walk through these environments really in large virtual environments? Why do we want to walk in virtual environments? Isn't it so much more convenient to sit at home with your controller, with a joystick, whatever, and you just navigate through that environment? It is convenient, but it has disadvantages. When we can really walk in a large virtual environment, it enhances the sense of presence. You feel more present, you feel more of being there. It enhances the perception of size and distances. You can feel the room, you can feel the size, you get a better perception of it. It can focus attention, you can look at things, you can walk there, you can look at things, you can interact with things directly. And it also, studies have shown that it improves task performance. We have a large lab at TU Wien, about 140 square meters, where we do most of our experiments that you will also see today. In 2015, we were approached by a German game company, Illusion Walk from Berlin, and they asked us to design a virtual reality system where multiple users can play and interact in VR arcade. You know it maybe as the Void or other systems that have all been developed pretty much at the same time. So we developed this system together with and for Illusion Walk, where multiple users can play together. You see a video here on the right. Users can walk around. We have developed a low-cost large area tracking system that I will present in a minute. People are animated and motion tracked. We also designed a virtual elevator where you can step on and change the floors. We had some form of simple haptic interaction, and people can use the space together collaboratively. So here is the system that we developed in 2015. Nowadays, these systems look much different, of course. Here we see that the hardware was still quite complex. User had a laptop on the back. The head-mounted display has a camera on top, and this camera sees the targets, the markers on the ceiling. So we developed a very simple low-cost tracking system with multiple markers that you can extend basically infinitely. There is also a motion capture suite, and it's multi-user, of course. The person can walk around, can study the environment with quite good precision simply by using these markers. And it's, of course, cheap because you just print the markers, put them up. So multiple users can explore this environment. The content is not the best. As you can see, we're not that great 3D modelers. And you can combine multiple rooms just by simply putting up these markers. We also have the elevator where a person can step on and then move to another floor. Then it gets interesting because you might have multiple people in the same real space, but they think they are in different floors and they cannot see each other. So how do you prevent collisions? How do you handle that case? That was a starting point also for the next research questions. People can, of course, share the experience if they see each other, talk to each other, and interact with each other. So that was the first prototype of our system, which is now being used in a couple of projects. For instance, we'll see one of the projects next, but here I would like to show you how we are mapping the environment. So one of the challenges is you put all these markers on the ceiling, but the next step is that you need the positions of these markers as precisely as possible. So one way would be to do measurements with a laser you know, surveying the room and measuring all the midpoints of the markers precisely. We have developed another method which is faster and requires less manual labor. We have developed a so-called photogramobot, a small robot on a robotic platform like a vacuum cleaner, and the robot is moving around and mapping the environment first, and then the robot is taking hundreds, thousands of photos of this environment, and we use standard photogrammetry software, reality capture, to process these pictures, align them, find common features. Here you can see the photos, and then create the 3D model automatically. And with this 3D model, we can then compute the midpoint, the position of the markers. So this is a very cost-efficient way of quickly installing such a system in any room. It's highly scalable, and that's important also for the company that they can install it anywhere quickly. We're using this system now in a number of projects, and one of them is a new project for the training of firefighters and first responders. You can see here, I'll skip the intro. This is with the Athens Fire Brigade, Athens Airport. We do the same in Berlin Airport. And they have a hall, again equipped with markers, and people walk around there. And the task is to extinguish a fire. So here you can see the firefighter opening the toilet door here, extinguishing the fire, and exploring the whole inner room of an airplane and extinguishing where necessary. There is also a fire simulation involved that realistically propagates the fire inside the airplane. And of course, that's much easier, and they can train much more often than in a real airplane that way. We also use the system now in Austria for medical personnel, EMTs, and firefighters. And we also have an outdoor tracking system now for using GPS RTK to have 1 centimeter precision outdoors. We have a combined system now, indoor and outdoor, where we can do both. We have used this system for scientific visualization, large protein networks. Even a Nature paper came out of that, which is very surprising for us because we're typically not publishing in these journals. And we have a FWF Sonderforschungsbereich about haptics, where we use that system, and we have used it for marketing and sales and other applications. So it's quite a flexible, versatile system and applicable to many fields. But the walkable area is of course limited to the size of the tracking space. We have a certain room size, we have a certain area covered by markers, and we can only walk in that area. If we want to walk through a cathedral now, like Sagrada Familia here in Barcelona, how can we do that? What do we need to do to make people walk through such large environments? Well, we will have to make users believe to walk in much larger spaces than they actually are walking in. And the first technique in this area was published in 2001 and is called redirected walking. Redirected walking is introducing some additional gains to the user's walk. For instance, translational gains, which means the user is taking a step. Let us assume step length is 1 meter. And instead of 1 meter, we move the user in the virtual environment by 1.2 meters or by 80 centimeters. And if this gain, this translational gain, is within certain boundaries, like 20%, users typically don't notice. So we can move them a bit more or less according to what we want. And the same is possible with rotation. If a user is walking towards a wall and has to rotate, we can make the user rotate much more in real, and in the virtual environment we show a lesser rotation. So users have to rotate more in reality and think, for example, here in the image below, they think they are walking like this, and in reality, they are rather walking back and forth in that small room. So these gains can be introduced. Here you see an example. Users think they are walking this S shape. In reality, they are walking an 8-figure. Other methods to trick users are change blindness. Here we see an example. A user is entering a room through this door, has to perform a certain task in this room. And when the user turns around and wants to leave the room, suddenly the door has changed position, but the user was so focused on his task, he didn't realize that the door is now at a different position, and you have successfully redirected the user from this direction to this direction. Another example are impossible spaces, where users are exploring a room, and when they are leaving the room, walk through the other room, both rooms overlap and the other room expands, and users do not notice this overlap in some cases. We will see very soon what the conditions here are and how this works. The method that we have developed in 2015 was this, no, that was 2013, sorry, flexible spaces. In flexible spaces, we let users walk inside rooms. So here on the upper right, you see the user walking in a 9 by 9 meter space. In the lower right, you see a top view of the environment. Here the user is in this room, exploring this room. And the user's task is to remember the objects that he sees. So he has a task to focus on content in those rooms, and he is supposed to explore this environment. So the user is walking through the room and exiting the room through this door here, and now a corridor is generated. The user follows the corridor, and suddenly another room pops up, and this room is overlapping with the first room, as you can see here. But the user has walked across around two corners at least, and when he enters the next room, he does not realize that it overlapped with the previous one. And that continues and continues, of course. You can create new corridors. The user walks through these corridors. There is another room, and it overlapped again with the previous one. If you ask users afterwards, how large was the environment, they are drawing up a much larger environment than it actually was. So what we are doing here is we are procedurally generating this environment. We have dynamically changing layouts. People can really walk, but the real world rules do not apply. You cannot build such environments in real. The focus is on the content, on the virtual content. The algorithm is quite straightforward that we're using. Based on one room, if a user is exiting the door, we place the second room randomly in the whole tracking area. The second room can also overlap with the first one. Then we generate the random intermediate point. This intermediate point must not be in the first room, of course, it must not be in the second room. And then we choose the door that is closest to the intermediate point of the second room. And then we calculate again randomly an additional point and have different solutions now, different corridor possibilities to walk to the second room, and we choose just randomly one possibility. You see, this process is highly random, which means the corridors are never the same that we create. But what are the properties of this environment? First of all, we can not draw a map, but we can draw a connection graph, because the connections between rooms are always the same. They are connected. One room is always connected to another room, but we don't know the real map. The room overlap tends to be unnoticed. Of course, this required further studies, and I'm going to talk about that soon. Successful navigation and search performance is possible. People can explore these environments and search, and the environment might be perceived as possible. And even if people don't perceive it as possible, they still accept it. It has different rules, like in a game. You're playing a game, you're submitting to that game, and you accept the rules of that game. Of course, you cannot do training scenarios, for instance, in such an environment. When you think of the raid of the Bin Laden compound, for instance, the American military built an exact replica of Bin Laden's house somewhere in the desert in a hall, and they trained specifically in that compound so that people know exactly the spatial layout. You cannot do something like this in such an environment, which changes dynamically. But you can do gaming, you can do tourism and museum applications where you explore rooms and content. So the next question was, do corridor connections influence the perception of rooms and the overlap? So what you are seeing here is two rooms that always overlap 50%. One room here is overlapped by the second room here. The overlap is in each case 50%, but users, of course, don't know that. And the rooms are connected now by different corridors. We looked at different number of turns. Here you have 1, 2 turns. Here you have 1, 2, 3 turns. And here you have 1, 2, 3, 4 turns. Then we looked at different endpoint locations. We looked at different turn direction sequences, left, right, right, left, and so on. And we looked at symmetrical and asymmetrical path. And we also did the same with curved path. And we wanted to know, how do people perceive the overlap depending on which path they walk. So here you can see a video how this study looked like. People started in a room. The user is immediately leaving that room, walking around a rectangular corridor here. You can see the real world environment below. And the user arrives in the second room. And now we ask the user, where was the first room? He has a controller, and with the controller, he can move and place the location of the first room. Here he detected some overlap. And if we look in average what users told us, so for these different corridor types, we got this result. You see here, this is the typical corridor. In average, we had no overlap between those rooms. There are corridor types where people think there is even more overlap. And very interestingly, this corridor type here, which is an impossible corridor, you can't do that in real, it crosses through both rooms and then goes into the other room. Here we have quite a large distance between both rooms. And then we did the same with curved corridors. Again, user is leaving the room. Of course, users do use different strategies to orient themselves, counting steps or remembering the directions or whatever. And here again, we ask the user, where was the first room? And the user is using the controller to place the first room. And the result that we're getting here is quite surprising. So here again, with curved, but immediately you can see that with curved corridors, we get larger distances, larger differences to rectangular rooms. And here the best result, or the result where we confuse users the most, is this S corridor, which again leads through both rooms into the next room. And we do not only have a distance in X direction, but also in Y direction. So that's quite exciting, because now we know that we can use different corridors to create different illusions and distances between rooms. If we look at the plot of distances, you see here below the different corridor types that we used. And in this S-shaped layout of the corridor, you see the blue is the X axis and the yellow is the y-axis. And of course, there is large variance in the results, but in average, we get 3.5 meters in x direction distance and about 2 meters in y direction. So that's quite impressive, and obviously the corridor type plays a major role in how people orient themselves and perceive overlaps and perceive positions of rooms. So to achieve the best spatial manipulation, use different turns in a sequence and use different distances also between turns. Always consider the walking direction, because interestingly, it makes a difference if people walk through a corridor in one direction or in another direction. Use asymmetric path and use curved path. And with these rules, you can achieve the best spatial manipulation. Now, after this study of individual manipulation of space for individual users, we looked at multiple users as well. How can multiple users efficiently use space? Why is this relevant? Well, if a company is building an arcade system, gaming system, they have a certain space available. Space is expensive, you need to pay rent, and they want to use that space as efficiently as possible, of course. So we looked at the different methods. How can people, multiple users in VR, use space? And here you see the systematic classification. First of all, there is co-located VR, which means that users are in the same tracking space and they also see each other in the virtual environment. They share the same virtual environment, co-located, shared VR. Next option is users are still in the same tracking space, but they are each in their own virtual environment. They do not see each other in VR, they just play individually. Next option, users are separated. They each have their own tracking space. For example, everyone is at home, playing in their own home. They are remote, and in the virtual environment, they still play and enjoy together. And the last option, some people are together in a shared tracking space, and others are alone in their own tracking space. So some are remote, some are together, but they still share the same virtual environment. And which implications does this have now? What are the differences? So we did different studies with different scenarios, and we looked at how do people perceive each other? Are they aware of each other? In this scenario, for instance, where they can't even see each other. Do we have to prevent collisions? If they are aware of each other, we do not need to care of collisions. So is that necessary even? What are techniques for collision avoidance? And then we also looked at copresence. So are they aware of other users in the environment, and how do they perceive them? And we did a couple of studies to investigate these questions. And I'm going to talk briefly about this study here and the last one where we had mixed collocation. So in this first study, we had this scenario where users are in the same environment, in the same tracking space, but they do not see each other. They perceive different virtual environments. And the task was very simple. Users had to walk close to each other or in opposite directions. And we wanted to see if users perceive each other in some way. Do they notice that someone is there? Even if they don't see each other in VR, they could notice due to airflow, heat, floor vibrations, maybe some smell of the other person, whatever. We had 36 users, 18 pairs, and the study looked like this. You see an example here. Here is one user following a bird, walking behind a bird, and another user. And they were instructed, if they perceive anything, point in the direction where you feel there is something. So this is a typical example. You see the user noticed something, pointed in that direction. These two girls are walking and don't notice anything, as you can see. And here they are walking next to each other and nothing. Some users even, here a little bit now, some users even touched each other and didn't notice. They were so focused on the virtual environment. And the interesting result here was that out of 36 participants, only 6 noticed another person. So what does this tell us? Of course, we must take care of collisions. People will not notice each other. Even if they are that close that they touch each other, they don't realize. So we must take care of collision prevention and find methods to avoid collision, warn users, whatever. There are different techniques to do that, which we looked at in another study. The last study that we did was with some people together in one tracking space and another person remote. And we wanted to find out, do co-located and co-located are these, and distributed players respect each other? Are they perceived differently? Are users able to tell which player is with them in the tracking space and which one is distributed? And will users walk through distributed players? Will they ignore their avatars, their virtual presence? So we had 17 triplets of participants, 51 participants in total. 2 were always co-located and 1 was distributed. We had 2 scenarios. The competitive scenario where they have to build 3 towers individually. Each user needs to build a tower and they share the same environment, the same space. Or the collaborative scenario where they all have to build a tower together. They were instructed not to talk to each other because if they would talk, they would quickly identify who is there and who is not with them in the same space. It looked like this. The blue and the green user are together in one tracking space. The purple user is distributed. The blue and green are here. And they have to, and you can see they always cross the middle here. They always cross the same space. So the task is set up so that they collide with each other. And here is the purple player in an independent tracking space. Now, what do the results tell us? First of all, users know pretty quickly which players are co-located with them. It's not really surprising, but users realize who is with them and who is not. Doesn't need talking for that. They perceive that and see somehow. The other interesting result is that users walk through the distributed players. So they have figured out who is with them and they walk through the player who is not with them. But women don't do that, only men do. And that was a very interesting result. We have seen gender differences here. Female participants report a higher illusion of co-presence, so they feel more present with other users. They are more aware and more careful. And there are different possibilities now how to explain this. One possibility could be that they have less gaming experience, and maybe that's why they are more careful. But reality is we have seen these gender differences. They probably need further investigation. I mean, we had quite a lot of users, but still. And this is interesting now also for training and team training and team gaming scenarios, because we noticed that participants mainly focus on the task. They don't focus on avoiding collisions. And this can be problematic if they have to do a team training task where they are supposed to feel that everyone is here. They have to do it together. And they don't have this feeling of togetherness if they walk through each other and don't respect each other's space. So it might impact the efficiency of such tasks. In summary, users are not aware of each other in a co-located space. This was the first experiment. If they cannot see each other, they were not aware of each other. And collision avoidance is important in such a case. The physical co-location, if they are together, influences how they perceive each other, how they perceive each other's bodies and movements. And there seemed to be a gender effect on co-presence, that women respect others in a virtual environment and don't invade the personal space or the personal avatar. Here we did another study now, which is adding the third dimension. So we wanted to find out, can we also simulate height in VR? We have built two bridges. One bridge is a flat bridge, the other is a curved bridge. And we wanted to see if we simulate now different height of bridges in VR, can we trick people into believing they walk on a larger bridge? We briefly see how this scenario looks like. Here a person is walking over a flat bridge, and here a person is walking over a curved bridge. And the person has to, people are careful, of course, walking. They have here a rail, and they have to enter in the middle of the bridge. How high is the bridge? What is your feeling? So just judgment. We have shown them different bridges with different height, and they were asked to enter the height. And the result was that with the flat bridge, people underestimated the height, of course, because they walked flat. So even if the bridge was very high, they still underestimated it. But it was possible to simulate a downward hanging bridge with this one. So we could show them a downward hanging bridge, like 20 centimeters downward hanging, and they perceived it as real. With the curved bridge, we could easily add or reduce it by 20 to 40 centimeters, and it was still perceived real. So if we have such a curved bridge, a curved surface in our virtual environment, we can simulate different heights. And finally, I would like to talk about our studies on haptics. So we have this FWF Sonderforschungsbereich about advanced computational design, and our work is on large-scale haptics. We can construct and design in virtual environments, and nowadays most production processes are virtual processes. So what if we do not only want to look at objects in VR, but what if we want to touch them, feel the material properties of objects? And for that, we are working with a mobile robot. This mobile robot here is presenting haptic resistance, haptic feedback. We started with a simple experiment in our lab where we used the virtualizer to walk on spot. And we had a very simple, rough robotic arm. And when the user walked to a wall, the robotic arm presented a piece of the wall, a wooden board, and the user can now touch this wooden board. And when the hand of the user moves, the wooden board is also moving with him. And that was the idea, to experiment with that in a larger area now. So this mobile robot is your personal assistant. He follows you wherever you go, and whenever you want to touch something, he's presenting it to you. So we want to design with natural haptic feedback in a virtual environment by using this Cobot. It's a collaborative robot, which means it has sensors that detect forces and can react to that. We also want to represent mechanical quantities, for example, stiffness of materials, elasticity, so that the robot is reacting depending on the forces that are in play. Most of our work up to now, the project is running now for two years and will go another 2 years. Most of our work has been invested into making this safe. How can such a robot interact safely with people, with multiple users in that environment? We have 2 redundant tracking systems on the robot and also track users, of course, to be sure. And I have another slide about that. And we want the robot to be able to anticipate where the users are walking next and where they want to touch next, so that we can be there fast enough. Here you can see the robot. This is a very early video when we got it. And It has omni wheels. It can drive in any direction at any time, which is very important that he can also get out of the way quickly. The user cannot see the robot. The user is wearing a head-mounted display. And if the user is walking to the robot, he must be able to move out of the way. So this is now the typical usage scenario. The user would wear a head-mounted display. The user would wear a head-mounted display and would not be able to see the robot. And robot would present a wooden board or any object. And when the user walks to the robot, it must move out of the way. Here is recent work that we did with path planning, safe path planning, if there are objects in the way or users, and different scenarios how the robot is supposed to react in a corner, for instance, so that the user doesn't get locked into a corner and the robot doesn't get locked into a corner, and how to position the robot in a in safety zones around the user. And we also need to take care of planning the movements of the arm in a safe way. Typically, path planning algorithms, inverse kinematic solvers, do not care if there is anyone in the close vicinity to the robot arm. So the path is planned, the robot is moving that way. But in our case, a user might be very close, and we need to plan the path of the arm in a way that we are not colliding with the user. So we have some specific challenges that are not typical robotic challenges, that are more VR related. And of course, as I mentioned, the user behavior should also be predicted so the robot can anticipate and be at touchable surfaces before the user. So the VR specific challenges are that we have unexpected user movements. Therefore, we need low latency in tracking and robot control. Fast robot movements in all directions must be possible at any time. We have close direct interaction, and we have multiple users in the environment. Therefore, we need very good safety measures and need to pre-plan the movements also for probable future interactions. And for the last point, we cooperate with mechanical engineers who do the planning of the forces to compute mechanical response of that material that we are touching. In summary, I've presented you methods how to enlarge walkable space with redirected walking and with our flexible spaces method. I have talked about collision avoidance and copresence in multi-user environments, what needs to be considered here. I've shown you some rather fun studies about adding the third dimension, and last but not least, I've talked about haptic feedback. Thank you very much.
Thank you, Hannes. Again, very impressive and very well presented. I think everybody who's not in the field of VR, I guess, still got the ideas. Any questions? Also, people online. Andreas?
Yeah, thanks for the talk. It was really interesting. On one image, you had this virtualizer, I think you called it. So, and I've also seen some videos online of these devices where people are harnessed in or run on or walk on a treadmill-like thing.
Yes.
How does this change the experience compared to actually walking in a room? So is this?
You can also see it here in this image here. Tunjai Chakmak is the developer of the virtualizer. He actually studied physics, but then he came to me and had this idea, and I thought at the beginning it's quite crazy and didn't believe in it, to be honest, but he completely was focused on it and followed his vision, and he developed quite a good product. Now it's commercially available. Many universities have bought it. I mean, first it was a Kickstarter campaign, you know, and he wanted to sell it for 700 euros, but I think the Kickstarter backers never got the product because it was much more expensive to produce, and now it's sold for about 5,000–6,000, I think. And the experience of walking in it is different, of course, than if you really walk. Any such locomotion device gives you a different impression. You are so used to walking, and all the sensors in our body are so used to it. What happens here in the virtualizer is that you have a slippery surface. You are in this harness, and you basically slide. You lean forward in the harness, and you slide with your feet over the slippery surface. So it's more, you feel the pressure on your hips, and you are sliding. The better you are trained, the better you, I mean, Tunja is running into it, in it and can do everything. And the more you are trained, the less you feel this pressure, and the better you can walk, but still it's a different way of walking. Nowadays he has a model which is tilted, so it helps you with the walking. It automatically introduces some tilt, so you are you're slipping more easily, so to say. Yeah, does this answer your question?
Thanks.
More questions, Mark?
Yeah, I have a question or two. Maybe I start with the first one. So all these enlarging environments studies, they rely on the underlying assumption that that it's beneficial to really walk in the virtual environment and to not just have a controller. Is that really the case? What's your take on that?
I think so, yes. I wouldn't do it if I didn't think so. I have observed users for over 20 years in VR, and first of all, I mean, the first main difference is a sitting and the standing experience. When you're standing and when you are free to move, you suddenly, you're more present, you're more immersed, you have better feeling of things around you. If you're sitting, it's a different feeling. Maybe you have experienced that, sitting against standing. The next big revelation or step was when we removed the cable from the head-mounted display. As long as we had a cable and people moved around, they were much more careful. They were aware of the cable, of the pressure here behind the head, and they were carefully moving. As soon as you remove the cable and people are cable-free, they move much differently and more freely in a virtual environment. And then imagine removing the how is it called, the grid that you have in virtual environments. How do they call it? You know, in HTC Vive, you always have this grid around you, which limits your experience. We always turn it off, so people can't see any limits. They can move freely now, they don't see the limits, and they can walk wherever they want. And this is mentally different, you know?
Yeah. I mean, it could also depend on how lazy the person is.
About what?
How lazy a person is.
Of course, and it also depends on the task. I mean, if you want to do something relaxing, you don't want to walk around. But if you have the task to do training, for example, a firefighter who needs to do training, if you do that in a sitting scenario, it's simply not the same, and it does not transfer. You always need learning transfer also to the real world. You don't have a learning transfer if he's sitting and doing like this.
Of course, yeah. And my second question is a meta question, so it's literally a meta question. You know, Facebook and Meta is working on this like VR metaverse, and they're behind the plans in terms of adoption and costs and everything. Do you think they will be able to deliver? I mean, it's like hard to predict, obviously, but you're an expert in the field, so what do you think?
That depends on the time horizon. I mean, these companies have a lot of money. If we are talking about 20 years, maybe yes. If we're talking about next year, no.
Yeah, let's see. They have the time.
They have the time. Yes, it depends on your expectations. I mean, we are working in VR now for 20 years, and I would not expect any sudden hype. And of course, it takes time until consumers pick up, but also for hardware to be improved. I mean, I've talked to a couple of companies now recently, which was rather a coincidence, but I know now multiple companies, they all work on AR glasses, which are to come out next year and in 24. So we will see advancements of hardware, mostly for AR, but also VR hardware will be improved and will get smaller. And yeah, I mean, it's a matter of time, it's a matter of hardware, it's a matter of user acceptance. So it will not happen overnight. And of course, we also need the network infrastructure. If you want to have thousands of people in a virtual environment, you need a good system.
Yeah. Okay, thank you.
Patrick?
Yes, thanks for the talk. My question is also regarding the perceived space. When you did this with the rooms and the hallways between them, was there a difference between the experience the user had with the VR kit? So some that experience with it perceive the space smaller, and those that maybe had no experience with the VR kit, that they kind of got lost a bit themselves and perceived the space much bigger. Was there some differences between the?
I'm not exactly sure what you mean, but of course there are always individual differences, but that's with any study. But what did you exactly mean? That users who have less experience in VR perceive
that, you know, you tested how much they thought their rooms overlap. And my question is, if those who didn't have experience with VR thought that maybe the rooms did not overlap or overlap more than those with experience. Did you notice there anything?
I don't know if we looked at that, to be honest. We probably asked for previous experience, but I don't know the result of that specifically. I'm sorry.
Okay,
I cannot tell.
Yeah, thanks.
More questions? Yeah.
Thank you for the lecture. Like, it was very insightful for a beginner like who doesn't know much about VR. But like one thing that is showed about the elevator. So when the elevator, like, it changes the floor side, and when the portion is like, let's say, coming down, does it, like, when we come down in the elevator in real life, we have this sense of like coming down? So is it
that you can so first of all, on the elevator we have a butt kicker. The butt kicker is a vibration motor. It's attached to the elevator, and when the elevator is moving, it's vibrating, so you feel some vibration, and then you can help the feeling with a ventilator, with the fan. So we have a fan on top, and the fan is producing airflow. So I mean, of course you can help and simulate and get a better feeling for this, but it's never the real thing. But people, you know, the thing is that in VR you can trick people into a lot, and the visual sense always overloads the other senses. So we see that, for instance, when there are haptic illusions. For example, you present someone, you give someone a glass, and you show them a vase, a curved vase, and people touch it, but because the visual sense is so much stronger, they really feel the vase. So, and with the visual sense, you can also overload the auditory sense, and you can overload perception. So if the visual sense is good, you can make people believe a lot of things. We have I always mention this example of the velvet wall. So in Berlin, Illusion Walk has this immersive deck, our platform installed, and they have different scenarios. And the lady came and tried it and was very impressed. And 2 weeks later, she came again, and she said she wants to touch the velvet wall. Where is the wall with velvet? And they told her, we only have concrete walls here. We don't have a wall with velvet. But she saw that in the virtual environment, and she was so convinced that the wall is velvet. It wasn't.
More questions? Also online? Any questions from people online? And there's a question from me technically. Tracking position, that matters probably. I mean, you have obstacles in your room. What do you do about limited position, that people don't hit columns in the room that are not because people are not precisely tracked?
Well, that also happens, but I mean, we use different tracking systems. In our lab, we use now an HTC Vive most of the time, and we use in combination our tracking system with the markers, but the HTC Vive is more precise. There are a couple of papers about it. You probably know we have millimeter and even sub-millimeter precision sometimes, but millimeter is good enough. And of course, you have to calibrate it each time again because of registration, so that the columns are precisely registered in the environment. But we can work well with an HTC Vive, and with our tracking system, you have seen some of the videos now where people are training in large rooms, and some of these large rooms don't have any columns, so we don't have problems. But yes, of course, we reserve some safety zones, usually around the column. We have a little bit bigger zone around the column, 10 centimeters extra, so that we don't have collisions there. But even with our tracking system, we worked a lot on that. The precision is quite good now. We have also 1 centimeter over the whole volume, which is okay.
Yeah, but the same applies to multiple people. When you need to track multiple people and collision avoidance, it's probably difficult to track the whole exact shape of the person.
With our tracking setup with the markers, we mostly track the head, and we have some sensors on the limbs, which is inertial. And of course, you don't have that precision. The problem is always when people interact, when one user is touching the other user, then it gets critical. But for that, we also use hand tracking now. A student of mine is working on tracking multiple hands. So when you know, some of these HMDs have hand tracking now embedded, included, and the Oculus Quest, for instance, and also the Vive. And when they see hands, they can track hands, and we can even distinguish which hand belongs to which user, and then improve our tracking precision.
And what's the feedback of the expert users, like the firefighters? Is that realistic enough for them? I mean, there is no heat, there is no smoke, there is not always realistic haptics compared to when they do this in a plane.
The haptics is the most different thing, yes. With the visualization, they are happy now, I think, from what I know. We can simulate smoke, but of course it's different too.
Yeah, I mean, there is no smoke, they don't smell it, they don't feel heat or fire. And
no, they don't feel heat. We are looking into heat simulation, which is actually not so easy. We have looked into different ways of producing heat with a heat cannon, for instance, that you use to dry things. And we have tried different things, but we're still looking into that. It is better than anything they have. And of course, it cannot replace the real training yet, but they are okay with it, actually.
Did they do training?
They do training. For example, there is this Dutch system, how is it called? There is a company, a Dutch company, which is very widespread in the whole European area, which provides online training. They have sophisticated models and training scenarios, and you can do desktop-based training. And they also have a VR module now, which is not that flexible. But yes, firefighters all over Europe are using that system for training.
Okay. Okay. Good. If there's no more question, also not from people online, then Hannes, thank you very much.
Thank you very much too. It was a pleasure.
And I hope to see you at some point here in Linz again.
I would love to, and you're always welcome to visit us as well, of course. Thank you very much.
Bye-bye.
Bye. Thank you.
Okay, so thank you for coming and joining. I don't know the next talk's date. Is that already fixed?
It will probably be the 24th of November that we're going to know.
You will be informed. Huh?